talk about that. So we'll fix it. Don't worry. Oh, then we'll just... So this is it. So this is That's totally fine. Here we go. I think we got view, correction. That's all we're doing. But this is reading corrections and right. All this is optional. I mean, and that's one of the reasons I gave you guys that survey on the last day is because I want to make sure that this optionality kind of stuff is like legit in your mind. It's like this is how you learn. That's exactly what I want to hear. I want to collect data so I can tell my boss, like, look, it's working. The students like this and puts their minds into this. That's all I care about. I want you guys in a situation where you can learn comfortably and kind of at your own pace. So, all right. Whew. Let's talk. So, project not due till next week. We got time on that one. I'll have the exam up ASAP. Like I said, I'm building it right now. I haven't posted it yet. It's coming together. It needs spreadsheets and stuff. And I mean, on the video, you'll see. Yeah, I guess that's it. That's it for now. You guys have any questions for me before we get back into what we were doing yesterday? Anything on your mind about assessment? What's due? What's coming back? See me a break if there's individual point questions, but other than that, feeling pretty good? How's week 7 treating you? It sucks? Good? I'm going to take that as it's okay. Put your head, your feet, put your head in the, put your head in the otis. Forget it. I had an analogy, I just ruined it twice. Done. It's a good one too. It's funny in my head. No. Ah, the hell with you. All right. Let's get back into this. Because I have some more data sets I want to play with, and then I have a data set I want you to help me create, with your permission, of course. The date? 14. 14. Sure. 14 sounds good. So, in class thus far, we've created three exponential models based on 3 different data sets. Some of you are thinking, what are you talking about? We did that? How dare you say that, sir? But we did. I had half the class flipping coins until you got heads. I had half the class pulling cards out of a deck until you got diamonds, I believe it was. And then at the very end, I don't know how the hell we came to talk about this. We played rock, paper, scissors, and we decided to model that one as well. What about lizard? Oh my gosh, I don't understand that. So, rock, paper, scissors, coins, cards. I have 2 more data sets I want to play with today. And then a 3rd data set we'll collect, and I don't think we'll finish it today, we'll play with it starting on Monday, to kind of take us down the remaining 3 weeks we have together, which is what I want to kind of culminate with an understanding of the game of craps. Because, and that might seem superfluous, but if you can understand craps and the way that Vegas pays out for bets at craps, you'll have a way better understanding, not just of that, obviously, but you'll also understand an awful lot how your medical bills work and how much you pay for car insurance and things like that. You'll have a better, everybody always tells you, you got a 16-year-old kid, 16-year-old boy, you're going to pay way more for car insurance. Now there's a very simple reason for that, if it's true. What would possibly explain it? You've got a higher risk in that age group of having a crash. The idea is, how do you metric it? So I think it's the common belief, although it might be urban legend. Like, there is an urban legend that says you pay more if you have a red car. That's been around for 30 years and it's completely false. But it's one of those urban legends that gets believed. If you have a red car, you pay more on your car insurance. It's bogus. It's totally bogus. The kid, the 16-year-old boy thing, I haven't checked into data-wise. But even if it's true, and even if the red car thing were true, how do you measure it? How do you measure how much more you should pay because you have a 16-year-old? You see what I'm getting at, friends? And that's where craps plays in. Because if you play craps in a casino, why is craps so popular in casinos?
The best odds without the house.
I love that. Damn close to that. Ryan, go ahead.
It honestly gives the player more feel that they have more control over the outcome.
And I think that ties in what Francis just said. It's got extraordinarily close odds of winning. The fairest game in a casino is not craps. You know what it is? Fairest game of chance, not poker. Poker's a game of skill. Roulette. Roulette's better. 49.8%. What's baccarats?
Huh?
What's baccarats?
Baccarat?
Go ahead.
Okay,
No. What's the edge?
I know, but I know it's the best one.
Well, let's figure it out. We'll calculate it at break. I know roulettes. It's got a smidge better than craps, but it's real close to 50-50. It's just a little bit below 50-50 though, which means you're going to lose your money. It's just going to take you the longest possible time to do that. So if Vegas knows that, they know how much to pay you when you win to keep you playing, but also keep taking your money. Does that make sense? So Vegas knows that, and if you can understand how craps works at the most basic level, you'll understand how your medical insurance, or your health insurance, and your car insurance work in the same way. So that's what I want to kind of head to, is that idea. Exponential modeling gets us there pretty cozily, actually.
So can we beat the house after those classes?
Not on a game of chance. Game of skill you can. A game of skill like blackjack. If you've read the movie, if you've read the book Breaking Down the House, or seen the movie 21, which is not quite as good as the book, but you can totally beat the house if you can count cards properly in a game of chance, in a game of skill, where you have some measure of control. I can't talk about things like poker, blackjack. If I guess 5-card stud you could talk about to some degree, because there's no trading of cards there. I don't believe in 5-card stud. I'm playing in what I don't understand fully. But things like roulette, one-armed bandits, craps, those are pure games of chance. You throw dice, you spin a wheel, you look at a card, and that's it. So I can teach you how to, what I can basically teach you how to do is how long can you play until you bankrupt yourself. I can teach you that. If you can take that and figure out how to use it to beat the house in other games, out of Math 105, of course. We don't have time to do all that stuff. That could be a course in itself. That's actually how that movie 21 started, if you remember. Who's seen that movie 21? A bunch of you! Did anybody read the book, Bringing Down the House, which it's from? It's a fantastic book. Much better. Nobody ever gets beat. FYI, nobody got beat up in real life. That poor kid got beat up. Was it the kid or the teacher that got beat up in the... It was both. Yeah, I saw that. I'm like, come on, Kevin Spacey. Nobody got beat up. But anyway, that started as an after-school MIT club. That whole thing started as a club at school. So, I mean, it's totally a skill you... And honestly, it's even easier math than we do in here. Did they explain it in the movie? I don't remember. Did they explain how they counted the cards in the movie?
Yeah.
Not very well. That's why you want to read the book. They had a code system. Did they explain the code system in the movie? When they would say something about eggs when the count was at 8. Oh, no, excuse me. They would say something about eggs when the count was at 12 because a dozen eggs. And they would say something like a stop sign. When they kept count of the cards coming out of the deck and whether they were big or little. And when a whole bunch of little cards were coming out of the deck, that meant there were a bunch of big cards left in the deck, hence card counting. And they had this series of code. If you haven't read the book, it's fantastic. If you haven't read the book or seen the movie, read the book first. Because it goes by so slickly in the movie that it's glossed over a little too much. And it's a beautiful explanation in the book of how they were able to beat. They actually made Vegas change, if I remember correctly. They made Vegas change the way they dealt blackjack. They used to deal with six decks in a horseshoe. And they stopped doing that because of these kids. Because there were so many cards in the deck and the kids were so good at counting them. It has to do with, next week, talking about randomness. So if you imagine 6 decks shuffled in a horseshoe, human nature wants them to be like 1 deck, 2 deck, 3 deck, 4 deck, but that's not what happens. They clump together, right? They clump together in places, and the kids kept track of that. And when they found it was the most advantageous to bet, they bet huge amounts of money. And more often than not, they won huge amounts back. Of course, they lost too. It required a lot of money to start, which is, I think, why an MIT prof started the club. I mean, those guys get paid $1 bazillion a minute. So he just fronted the money, and then they made even more money back. Yeah, Ryan, go ahead.
I'll just explain the entire thing really quickly.
Go ahead, please.
Any card below an 8 was considered a +1. Any card above was a -1.
Anything else was 0.
Yeah. So whenever they got up to a point above 10, they would call in the second person to come play, because at that point there were more 10, 9s, and 10s.
There were more large cards in the deck, which is what they wanted.
Yeah.
Yeah, so essentially...
So they're keeping track of the odds as they were going through that.
But, and there's nothing illegal about doing that in a casino.
It's just frowned upon.
But the casino, it pisses them off when you do it. And they ask you to leave. Remember they were getting beat up in the movie? Yeah. Nobody got beat up, they were asked to leave. So they wore disguises.
Yeah.
They wore crazy disguises. And what's amazing about it, it's just gorgeous. I watched a TV show years ago about cheating in Vegas. And there's this one video of this dude wearing a parka in like July in the casino. And the reason he's wearing a parka is because he had a little camera on in his sleeve that was taking a picture of his hand, and the dude, I don't know how the hell the other guy had a camera too, and he was, that's cheating. Because he was basically looking at his hand plus other cards and telling the player what to do. He's in a parka in Vegas. I mean, it's 110 degrees in the shade. Last time I was in Vegas in July, I was in a van on tour. I was in my underwear with the heat turned on because the engine was going to explode. This guy's at a parking. It makes me sick just thinking about it. So that's obviously cheating, but card counting is not. It's a skill they don't want you to have because you take their money from them, and they don't want that. You can't give people free drinks all the time if you keep losing money. So anyway, it's a great book, fantastic book. And it's tied directly to what I want to do the remaining 3 weeks we have together, which is basically understand craps a little bit better. Good, we'll start today. Anyway, I want to wrap up exponential modeling though first, because this is believe it or not, this is the first step towards that, and you'll see how momentarily. We had 3 models. We had the flip a coin until heads. We had draw cards until diamonds, yeah. And then we had rock, paper, scissors. Stop it. So, in these two, we actually had run data and then come up with a perfect model. In the last one, we just went straight to the perfect model. And I asked a question at the end of class last time, we never got the answer, so I want to answer that today too, of course. So, flip a coin until heads. There were 200, I think it was 289 of us flipped coins, correct? So the model for both of them was y equals 289, excuse me, that was the perfect model, 289 times 1/2 to the x power. That's the perfect model. That's the model that we came at after the fact. Now what this means is every time someone flips a coin, right, what happens on that coin? Or what could happen on that? Let's say, what could happen on that coin? It could be heads, it could be tails. So if a bunch of people flip a bunch of coins, describe roughly what's going to happen to that bunch of people. Roughly. So if everybody here took a coin and flipped it right now, which I'll have you do momentarily for a different data set, what's going to happen to a bunch of you?
Half of you are going to leave after a mistake.
Do we hear this? Half are going to get heads and half are going to get tails? So when x equals 1, otherwise known as 1/2, you take half of 289, and that's going to remove half of the people from the mix, because half of them are going to get heads. But then half of them are also going to get tails. Does that make sense, hopefully? Okay, so the half that got tails, flip again. So now we're down to about 144-ish, somewhere in there, 144 people. What's going to happen to those 144?
Half them get heads, half get tails.
Does that make sense? Half the ones remaining are going to get heads and half the ones remaining are going to get tails. So that would be 1/2 to the second power, second flip, which would be 1/4, which would essentially be dividing 289 by 4, which would get you in the exact same place after 2 flips, wouldn't it? So now we're down to about 72 people. What's going to happen on the next flip? Half are going to get heads, half are going to get tails, right? Half heads, half tails. So now we're down to 36 heads, 36 tails. The 36 heads are done. 36 tails, we're going to have them flip again. What's going to happen to them? Half are going to get heads, half are going to get tails. Now we're down to 18. Flip again. 9, flip again. 4.5-ish. Call it 4 to make the math easy. Flip again. 2, flip again. Flip again. Flip again. Flip again. Answer my question, damn it. Flip again. Good. So a 4th, an 8th, a 16th, a 32nd, you'll never get this here because it's asymptotic. That was the problem, of course, with the model versus the data, is it becomes a little bit fictitious. So we dealt with that, right? We took the zeros out. That deals with the fiction. It makes the model fit the data better. But the idea is this fraction just keeps changing every time this increases by 1. It goes from a 1/2 to a 4th to an 1/8 to a 16th. And that keeps multiplying by your original number. And that tells you how many are left after a set number of flips. Is that believable? If it's not perfectly clear right now, it will be soon, and if it's not perfectly clear soon, I've got a quiz that's going to walk you through it for next week that'll get you back into the mechanics of it and hopefully walk you through it even better. Now, our model that we developed in class wasn't this. I think it was 267, right?
Mm-hmm.
If I remember correctly?
Yes.
And it was like 0.53
Yes.
to the x power? That's damn close, isn't it, friends? That's damn close. 267 is close to 289. You might say it's not close. I say mathematically it is. I mean, holy crap. Remember, the TI that ran that regression had no idea that we were actually doing coin flips. It just looked at the data and said, oh look, if it continues in that way, the best guess I have is 267. I mean, it's almost vertical at that point. Any little shift, if you think about it being almost vertical, Any little shift is going to send it a lot further up the line or a lot further down the line. So I'm stoked it was that close. So you get an approximation. This is about 50%, just like that is. Could we get it more refined, do you think? Could we get the model, could we get this model to get even closer to this one? How do you think we could? We could make these numbers match these even more. We did 289 trials, right? How can we make our model that we got with the TI even better to the true absolute theoretical model? Say that again? No, I'm saying that I want to run this model again. How could I get a? Let me ask you a better question. I'm asking a crappy question. Suppose I want to know who is going to win the next ASCOCC election. Actually, I can't do it. Nobody's actually running right now. Next presidential. Is somebody running now?
Yeah.
Okay, good. Is it one person?
Me? No, I think there's 6 people.
There's 6 people. Beautiful. Thank you, Ryan. Up to like a week ago, there was nobody running at all.
Yeah.
6 people running. And I want to know who's going to win for president of ASCOCC. Blake, who are you going to vote for? Make up a name.
Trevor.
Trevor. Tim, who are you going to vote for? Make up a name. Julie. There's a 50% chance Trevor's going to win the election, and the other 50% is Julie is going to win the election. And I'm going to publish that result in a magazine. And I could do that, of course, because it's statistics, and I can put anything I want in a magazine. It's the internet. America. Now, what's wrong with my sampling methodology? You say that again?
It's not accurate.
Why is it not accurate? I asked 2 people, and you both gave me fictitious names. Say that again?
There's 6 people running.
But these guys voted for their favorite. What's wrong with the sample 2, Kelly? Does that bother anybody that I asked 2 people and I'm reporting on that? So how could I get a better model of what's actually going to go on? Ask more people. How could I get a better model?
Get more data.
Flip the coin more. Keep flipping. As you keep flipping, the model will refine itself and you'll start seeing this close in on the true values. I only had you flip about 300 times. Although that seems like a lot, it's not that many in the grand scheme of things. There's a lot more we could have done. Thousands of trials. In 243, should you go down that road with me, we do a lot of Excel simulations that do just that for us. Yesterday in class, I had the kids rolling a pair of dice, a single die, a pair of dice, and 3 dice, and flipping coins. And while they were doing that, I was having Excel do the exact same trial. In the time it took them to do 200, Excel had done like 200,000. And what's beautiful about that is, it's still not perfect, but it's perfecter, if that makes sense. So it might not be 260, it might not be 289, but it might be 282. And it might not be 0.5, it might be 0.4998. But at that point, you're like, oh God, it's close enough for government work. Does that make sense? Good, believable. Okay, now tell me something about these numbers. These particular numbers here serve the same purpose, and these particular numbers here serve the same purpose. So tell me about these 2 things. What do they tell you about the experiment you just did? How about the 267 or the 289, either one of those numbers? What does that tell you about the experiment? We got to vote for how many people did it? I love that. No, that's perfect. Now, some of you are going to say, wait a minute, there were 289 people in the room. But it's kind of like 289 people each took a coin and flipped it. 289 trials is a way to get around the language problem with that one, right? So I love what you said, Randall. It's correct. Imagine 289 people each flipping a coin. But you can also say you ran the trial 289 times. And that's what popped out. So if you start with 289 flips, or in this case 267, which is the best guess. Good. Remember what we called that?
Y-intercept?
Oh, perfect, yes. I wasn't thinking mathematically, but that's mathematically what it is. Because that's when x equals 0. X equals 0. Y equals 2. When x equals 0, that's the y-intercept. Perfect, Harry. Yeah, if you let x equal 0, that becomes 1 y-intercept. Beautiful. I was thinking contextually, but I love that. The y-intercept. No. I think we call it the initial value, I think, or the starting condition or something. I forget what language we used exactly. Initial value. Yeah, thank you, Joanne. Initial value. We start with that. And then we go from that, and we see what happens over a period of instances. What's this? Right, I was calling it the maintenance rate. The maintenance rate. It's the rate that is maintained with each successive trial that we do. So each trial, no matter what trial you're on, you're going to maintain the residuals at this percentage, 50%. Now you guys just told me that, although you might not like the word maintenance. But think about it. Speaking of which, summertime's coming. Make sure you get your oil changed in your car if you haven't done it in 5,000 miles. Not related to mathematics at all, really.
Oh.
Right? 5,000 miles, that's still what we use? 5,000? Yeah, good. Sorry, tangent. Public service announcement.
3,000.
3,000 miles, sorry. If you got a diesel, you can go longer with synthetic oil. But the point is that no matter what trial you're on, you're going to maintain 50% of the people in that trial. Because half of them are going to flip heads and half are going to flip tails. You're going to dump half and keep half. You're going to maintain 50%. Does that make sense? Hopefully that makes sense. Please, Tammy.
If you were actually doing
Yes.
trials, though,
Yes.
each time you get to the half, you would get to 0 because
Because eventually somebody's going to stop flipping tails.
yeah.
No, I see what you're saying, and what you're talking about is the difference between the real data and the perfect mathematical fit of the data. That's why we have to dump the zeros off. When the y equals 0, we've got to dump it. The model only gets us so close to the true data, but it gets us close enough to use it arguably, to predict what's going to happen. Suppose you see, very often you don't see the entire spread of data, you see part of the spread of data, and you want to predict what's going to happen next. Hence me and the Ben PD a few years ago. I could see what was happening with Ben's population, and I did a pretty good job of approximating for the next 3 years. But then other stuff changed, and the model changed. Ben went through a period of explosion, as you guys probably remember, and then it kind of leveled off and dropped off a little bit, and now it's kind of doing this fluctuation as we sit here. So the models can change, but when you're close to the data set, you can extrapolate a couple out and be okay usually. It's kind of like forecasting a hurricane. You've ever seen, well, I don't have hurricanes on this coast, do you have typhoons?
Tornado.
Tornadoes? Ooh, we have tornadoes? Oklahoma does. I'm thinking of in hurricane tracks, when they look at hurricanes off the coast, they'll show you the positions of the hurricanes, and then they'll try to predict where it's going to go next. And what they show is they show the tracks, and the tracks widen for each successive day that goes out because there's more and more uncertainty. Butterfly effect, weather, wind, all kinds of other variables. So what I had to do was try to do the best I could to predict for 10 years, and I told Captain Porter, I'm like, I can't do 10 years with any kind of accuracy. I can give you like 2 or 3, no problem. And I gave him 2 or 3, and they actually fit pretty nicely. But after that, it just became noisy. Because who was expecting well, it's kind of a rule. Who was expecting the market to collapse? Well, anybody paying attention would, because they couldn't grow like it was growing indefinitely. Eventually, houses are worth $8.2 million and increasing every 3 days.
Yeah.
But at that immediate future, it was still climbing like that. So it was pretty fair for me to say, oh, it's growing at 5%, it's going to keep growing at 5%, at least for a couple more years, until like everything kind of settles in and then it levels off. More on that leveling soon. I've got a fun model. We'll do a leveling model too in a minute. Yeah, Michelle.
So if you're taking out, so
The y equals zeros?
well, we're having 289, and some of them may be 0. So you're taking out some of those.
When you say some of them may be a 0, what do you mean?
Like we have 22 trials,
Yes.
and some of them are actually zeros where it didn't come up with anything.
I don't. You either got heads or tails though.
Like one of the projects, the one that you had on for the
Didn't get a 3.
TI. About didn't get
Right, but if you didn't get a 3, you've got something else.
Well, and if you didn't get a 3, when your number
You
got
keep
low-
going. Then you're maintained. Then you're maintained.
Okay.
Yeah?
But then if you're having this and you're going, okay, well, I ran the trial 22 times, and I have a 0 on this one.
But you can't get a 0 though.
Well, yeah,
There-
but then you just have however many people's left, so it doesn't matter if you.
Right, you either got a 3 or you didn't get a 3.
Right. That's what I'm saying. If you didn't get one, then you have
You
to.
keep going.
But when we were running
Mm-hmm.
when we were running the
Keep
the
track of all your
stats,
data. Mm-hmm.
When we were running the stats and we had the 0, and you said take out the 0 because it's going to really screw up your results.
Great.
Then it becomes an approximation.
Well, the whole thing's an approximation. It's a best fit curve. It's the best average
Not all
fitting
of the
curve.
data is in there.
No, none of the data is actually on the curve. If you guys actually took this model and plugged in the numbers 1, 2, 3, 4, 5, you won't actually get what we got in class exactly. You'll get close to what we got in class. The whole thing's an approximation. That's why I don't feel bad pulling the 0 out, because you're not sacrificing any kind of precision by yanking this. It was already almost a 0 anyway. So don't feel bad about
Pulling
that.
that out, does that make it to where it never actually reaches 0?
Oh, no. Well, technically speaking, yes. That's why the model gets pissed at you when you leave 0 in. It gets pissed because you're telling it has to go to 0, but it knows it can't. So by removing the 0, here's the pattern. Here's the pattern with 0. Here's the pattern without 0. Did you change the pattern? No, the pattern's still there. Taking the 0 out was just a mathematical oddity. Not an oddity, but a consequence. So by taking it out, you don't change the pattern. If you took out, remember I screwed up my data entry? You guys caught it yesterday. I think it was with the cards. I put in like 75 when it should have been 57 or something like that. That would have been problematic if I had put the wrong number somewhere in the pattern, because mine went like this, where it should have been like this. And that little hiccup right there, the TI is going to try to make the curve bend up to catch that. That would have been an issue because that's within kind of the formative curve of the pattern. The one at the end is meaningless almost. At that point, it's so small that it really doesn't do anything. Thank you for that question. Very, very good. So because it's an endpoint, you're not losing any kind of precision there. Speaking of the cards, what was the model we got in class with the cards? With your data that we fit to the curve. Anybody remember y equals
Something right.
something or other times something or other to the x?
It's like 2 right. Exactly. 2 machine 1/4 to the x.
Go ahead, take a look. You guys have it written. I didn't write it down, and I lost the data in 243 yesterday.
219, 2.68.
219.68 to the x?
Yep.
Thank you, Ian. That was the model we got in class. The 219 tells me approximately how many started pulling cards? 219, right? I know there was only about 15 or 20 of you doing it, but you did it repeated times, correct? So imagine you were all in a row, 219 people in a row with a deck of cards, and you were pulling cards out one at a time until you got diamonds. This would be how many were left after a certain number of trials. 0.68. 0.68 is the, again, maintenance rate. We're maintaining 68%, which means we're losing whatever's left, right? 32%. We're losing 32%. Now the actual model, the perfect model, if I remember correctly, and correct me if I'm wrong on this, was 218.75 to the x. I think that was the actual model. Let's say yes, you remember correctly. That's just insane to think that I remember something. Now, it's close. It's damn close here. Damn close. It's close-ish here. It's not as close as I would have liked. How can we make it closer? Again? Do it more. Although I would never make you guys run that. That experiment was more time-consuming than the coin flip, correct? Because you got to shuffle the cards each time, and you're stopping when you get diamonds, which only happens how often?
Whenever you get a diamond.
Think about that. Think about that cards. How many suits in a deck? Suits are the shapes and the 4 suits, right? Clubs, spades, hearts, diamonds. How many of each? That's the important thing to hear is equal amounts. There's 13 technically, but the key is equal amounts, which means you're just as likely to pull diamonds as you are to pull hearts, as you are to pull spades, as you are. I'm having a hard time saying that sentence. Yes, equal amounts. Thank you. Equally likely. Which means what? Go ahead, Tammy.
So I'm noticing that no matter how, so there's 4 suits, so you have a 1 in 4 chance. There's 2 sides, you have a 1 in 2 chance. And on anything you do, that's how it's going to be.
You're making the connection. We're going to lose 1/4 people each time, right? Yep. Right? Because 1/4, assuming you have 20 people. Chloe, I'll get your question in a second. If you have 20 people, how many would you expect to pull diamonds out of 20?
5.
You'd expect 5, right? 1/4 of them. And you'd expect the other 15 to not pull diamonds, so they would pull again, correct? Then how many of the remainder would pull diamonds on the next pull? Whatever 15 divided by 4 is, right? Whatever that is, a little less than 5. Does that make sense? So, why do I call this the maintenance rate? Because you're maintaining 75% of the population with every iteration. You're losing 25%, but you're maintaining 75%. 75% are being left behind, 25% are being dumped with each trial. Is it perfect? No, not in our data, because our data said 68%. It's damn close though. Chloe.
So, how would you know that 218 would be the perfect number?
Well, because I knew you guys did 218 trials that day. I actually had the numbers in Excel.
Okay, and so, but with the data that we put in it, we got 219.
Correct. The data thought it was 219, which was ridiculously close. So, when it mathematically fit the curve and bent it through the points you guys had, it hit at 219. Where you guys actually were at 218. So remember I said these were close, but they were off by 20 or so?
Yeah.
Off by less than 1? That's ridiculously cool.
Okay.
It's just that your rate was a little bit off. And again, we can refine both of that with more trials.
And you only know that number because you were keeping track.
Yes, ma'am. But that's how we got this model, was because I ran the curve through your data.
Okay.
Is that fair?
Yeah.
Good. Thank you. Fair enough? So in both of these, I'll circle the theoretical with red, theoretical and theoretical. Hopefully you now understand why they're the theoretical ones. If you know something about the deck of cards, and if you know something about the coin, as Tammy, you just said, well, since there's 4 suits and you're losing a diamond, that means 3/4 of the suits go through. What's 3/4 as a fraction? Or as a decimal? 0.75. And since there are 2 sides on a coin, heads you stop, tails you keep going, that means half of the sides go through, half 0.5. It's perfect. Now with rock, paper, scissors, we didn't actually run the data, although we can do it here again in a second if you guys want. Rock, paper, scissors, there were, let's just play again. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 36, 37, 38, 39. Almost 40 people. That works out pretty well. 39 people in class. 39 people in class. So that's what I'm going to start. That's going to be my multiplier out front. That's my initial condition, my initial value. And remember, I told you this story. I don't know how we got talking about rock, paper, scissors, but I said this is a way they pull a volunteer from the audience in Japan.
Randomness.
It was random. It's correct. I forget rock, paper, scissors came in. Because it's my brain and it's the way it works. Do you remember what the maintenance rate was for rock, paper, scissors? Do you remember? It was 2/3. Because if you think about it, when you play rock, paper, scissors with someone, there are 3 things that can happen. You can win, they can win, or you can tie. And we actually made a list in the board. In case, I'm going to do this kind of quickly because it's on the video from Monday. I drew a tree diagram, kind of like what you need to do for your project next week. And it shows you. You can either go rock, paper, scissors. Paper, rock, paper, 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 scissors. Scissors, rock, scissors, paper, scissors, scissors. This we did in class. I'm doing it quickly. 3 of those are ties. Scissors, 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 rock, rock, paper, paper. Got to dance it too. There's 3 out of the 9, that's 1/3, are ties. 3 of the 9 are wins. Rock breaks scissors, paper covers rock, scissors cut paper. That's 3 out of 9 are wins. And of course, for Blake coming to me, the exact same 3 would beat me. So you've got a 1/3 chance of winning, a 1/3 chance of tying, and a 1/3 chance of losing. The rules we set up in class were, you all play me, correct? And if you beat me or tie me, you keep going. If you lose, you stop. So, if you lose, what's the chance of losing? We just discussed it. There's a 1 in 3 chance of losing, which means there's a 2 in 3 chance of not losing, which means that's what I'm maintaining, yes? That's what I'm maintaining as we go trial to trial. So now my question is, based on 39 people, how many games would it take to get down to just 1 person on average? I'm going to leave this question for us. We take our 5. Try to solve it. Go take your 5, get some air, get some water. Try to figure out how many games on average would it take to get down to 1 person. And do it any way you can. Equation boot camp, trial and error, Ouija board, whatever you want to do. And then we'll model it and we'll see if it works. And then we'll model it.